Hello everyone. We are studying the asymmetric synthesis, which is one of the course of the M.Sc second organic chemistry. In that course, we have studied the number of the strategies reactions under the asymmetric synthesis. So now we are going to study the last point from this topic. It is the directed Aldol reaction or diastereoselectivity in the Aldol reactions. So up to previous lecture we have studied basically the three named reactions under the asymmetric synthesis, which are Sharpless epoxidation, then asymmetric hydrogenation, and third is the asymmetric hydroxylation. So in that cases we have used the chiral ligands. That chiral ligands will form the complexes with the metals and that can carry out the asymmetric synthesis, and thereby we are getting the single enantiomer. So now we are going to study the one of the name reaction, how we can direct the synthesis or selectivity in the particular synthesis. So example is the aldol condensation reaction. Now we know that the aldol condensation reactions, aldehydes and ketones that having the alpha hydrogen atom or the enolizable hydrogen atom that can react with the another aldehyde or ketone at the carbonyl group, and we are getting the beta hydroxycarbonyl compounds which are called as the aldol. So aldol condensation, it is carried out in presence of the base. We have know this reaction. The base abstract the alpha hydrogen and carbanion is formed at first, and after the formation of the carbanion it will attack the carbonyl group. We know that reaction, and we are getting the beta hydroxycarbonyl compound. It is also called as the aldol. We can see here reaction, we can remind the reaction. For example, this is the aldehyde. Okay, general reaction, general R group we have taken, we have not taken the specific group because we are going to study the stereochemistry or what will be the selectivity in this reaction, what will be the selectivity for the product in this reaction. So first we consider the general aldol condensation that involves this one enolizable carbonyl group. This is the enolizable carbonyl group, and in presence of the base like NaOH, KOH, etc., or in specific aldol condensation reaction, the modified reactions involves the use of strong bases, because strong bases will completely convert the reactant material into the enolate ion. Now let us see first general reaction. This contains these alpha protons. These are acidic in nature, so base can remove O- ions generated from the base, can remove this acidic proton. Carbanion is generated at this position, and this carbanion, it is very well stabilized over this carbonyl group by the resonance effect. So this carbanion, it is nucleophilic in nature. It may get converted into the enolate ion. This is the enolate ion for the corresponding, or we can show in here the enolate ion for this carbanion. This is the enolate ion. Okay, this enolate ion, it is nucleophilic at alpha carbon atom. So this carbanion and enolate ion, these are the same, having the same reactivity. Only difference is that we have shown these as the corresponding lithium stabilized enolate, and here is the ketonic. So tautomerism type of the reaction can be shown here, or this lithium may be replaced by the hydrogen atom. So this carbanion is nothing but the stabilized enolate ion. So this is the lithium enolate, or it is the Z enolate. Now this is the enolate we are going to study generally, and this enolate attacks the carbonyl group. So after attacking the carbonyl group, we can show here. This is aldehyde, which is highly electrophilic in nature. So after attack, what happens? This compound is generated. R, this carbon becomes, this oxygen becomes O minus, this carbon get attached to this aldehydic proton. So this is aldehydic proton carbon atom, and this is carbon atom from the enolate ion. This is the, we can indicate here by dots. So dotted carbon, this is from the aldehyde, and this ring carbon shown here, it is the nucleophilic carbon from the enolate ion. So new bond is formed between these. So as soon as new bond is formed, the chiral centers are generated at this position. So this is the basically the general product obtained in this aldol condensation. We are getting the OH group at this beta position. This is alpha carbon atom with respect to carbonyl group. This is beta carbon atom. So this is the beta hydroxy carbonyl compound is obtained. It is also called as the aldol. So that's why reaction is known as the aldol condensation. Now this is the simple reaction, basic reaction, but when we go for the, in order to study the stereochemistry for the reaction, we can observe here two chiral centers are generated. So due to formation of the two chiral centers, if we try to determine which type of the stereoisomers are formed in this reaction. So if two chiral centers are present, we know that how many stereoisomers are produced, 2 raised to n, where n is equals to the number of the chiral centers. So this chiral center is equals to 2. So 2 into 2, it becomes 4. So total 4 number of the stereoisomers are produced in these reactions. So we have to consider these two chiral center that will generate this product. It is not formed as the single enantiomer. It will shows the formation of total 4 stereoisomers. So total 4 stereoisomers are produced in this reaction. So how it is very difficult to separate the stereoisomer, and it is not possible. So yield of the reaction it is very less, and it is very difficult to separate the stereoisomer. So in order to direct the selectivity for the synthesis of the particular 1 or 2 stereoisomer, generally 1 stereoisomer, and we know that in asymmetric synthesis we are always synthesizing the single enantiomer, but in this case we are getting the 4 stereoisomer. Now first let us see which are these 4 stereoisomer, and then we will consider the corresponding selectivity for this reaction. Now if we consider this reaction, 2 chiral centers are generated and these 4 stereoisomers are formed. One compound first, second, third and fourth. Now let us see carefully the structure of these compounds. Here the 2 chiral center corresponding to this beta oriented groups are present. So this R2 and OH group, these are beta oriented. These are syn aldol. We can say this as syn because R2 and OH groups are present on the same side. So this is the syn aldol. We can call this as syn aldol product. Now the another possibility of the product, it may be the anti. So here OH group is beta oriented, R2 is the alpha oriented. So this is the anti product or anti aldol is formed in this reaction. So these two are differing in the configuration here. So these two are the diastereomers of each other. First and second, these are the diastereomers of each other. But if we consider compound, now first and second, these are the diastereomer because they are having the opposite configuration at one of the carbon atoms. So they are the diastereomers. They are having the different physical and chemical property. Now the another, and they will exist as the enantiomeric pair. So these two first and second, these are the diastereomer, and again they will exist as their enantiomeric pair. So we have to write the enantiomer for compound first and enantiomer for the compound second. So enantiomer is given as, this is beta oriented groups are present in syndiol. Here is alpha oriented groups are present in this another enantiomer. So compound first become one enantiomer, and this compound third, in which these two groups are oriented alpha, having the here alpha oriented groups, these are said to be enantiomers of each other. So these first and third are the enantiomer. They will exist as these two diastereomers. They are exist along with their enantiomer. Now another diastereomer is also existing with its enantiomer. So what will be the enantiomer of this compound? The OH group here is beta and R2 is alpha. So in enantiomer what happens? Opposite configuration is there. So where opposite orientation of the group is there. So this beta OH group becomes alpha OH and this alpha becomes beta. So these compounds second and fourth are the enantiomers of each other. So in this way we are getting the 4 stereoisomeric products are formed in the Aldol reaction. Now first we have to control the diastereoselectivity in the reaction. So we have mentioned here diastereoselectivity in the Aldol reaction, also called as the directed Aldol reaction. So we are directing the reaction in order to form the particular diastereomers only this reaction, and further we can direct this diastereomer into form the single enantiomer. So reaction further becomes the enantioselective. As the diastereomers are formed, so reaction will be diastereoselective, and when we form the single enantiomer from this diastereomer, it becomes the enantioselective or asymmetric reaction. Now in this case the rate determining step is the enolate formation and its attack on the carbonyl carbon takes place. So formation of this enolate ion, it is the slow step of the reaction or rate determining step. So in this case when we consider the formation of the enolate ion, here the two types of enolates are found to be generated. So first is the Z enolate and another will be the E enolate. Now let us see how it is formed. You can consider the same reaction RCHO, and we have labeled this adjacent to carbonyl group R1 is there and next is R2. So we have considered the same here. So these two types of the orientations or the enolates are formed here. So this double bond, this is formed by with the lithium diisopropyl amide. This is very strong base. This is the structure of the lithium diisopropyl amide. This is bulkier strong base. Why we are using this strong base? Because if we use the NaOH or KOH, in that case what happens? The small number of the enolate ions are formed. So as the small number of the enolate ions are formed, they may get revert back to the reactant. So we are not getting the high yield of the product in that case. So we have to firstly convert all the reactant molecules into enolate, 100% enolate, and then we treat the electrophile or the carbonyl compound with the enolate. So we will get the maximum yield. So in order to get the complete formation of the enolate ion, we are using this strong base, lithium base. It is lithium diisopropyl amide that will generate the lithium enolate. So this is lithium enolate. Again there are two types, Z enolate and E enolate. Now let us see this formation of the Z enolate in the medium. When we are adding this, both enolates are formed, Z as well as the E enolate. This Z enolate, it is reacted with the aldehyde and it is found that this gives the syn aldol as the enantiomeric pair. This diastereomer is produced. When we use the Z enolate, we are getting the selectively syn aldol formation. So this is the diastereomer, and this diastereomer exists as the plus minus pair or the enantiomeric pair. So this is the racemic mixture of the corresponding enantiomer. So we are getting this single diastereomer. When we use the E-enolate, second is the E-enolate. When this R2 group, so this R2 group, it is the higher priority group in this case, and oxygen having the higher priority. Z and E form, we know that this carbon having the oxygen as the higher priority, and for this carbon R2 group is having higher priority. So higher priority groups are present on opposite side. So this becomes the E-enolate. This is the E-enolate is formed, and E-enolate will give rise to the anti-aldol product. Anti-aldol product is formed. So we can see here, we can observe here, when we use the Z-enolate, we are getting the syn-aldol or syn-diastereomer, and when we use the E-enolate, we are getting the anti-aldol. So what is our job? We have to first synthesize this enolate, then trap this enolate with the particular reagent and separate them by the column chromatography, and again we have to deprotect this enolate so that we will get in the pure form. For this we can apply, we can use the corresponding strategy. We can use the trimethyl silyl chloride compound for this. So we can write this structure, directly write the structure of this Z-enolate. It is the Z-enolate. It is formed in the reaction along with the E-enolate. We can see here, this is the Z-enolate and it is the E-enolate. Now these both enolates are produced when we are treating this aldehyde with the ketone in presence of the strong base. Okay, so in medium now both enolates are present, and we can trap them by using the trimethyl silyl chloride. It is also called as TMS chloride. It is trimethyl silyl chloride compound. So this type of this silyl compound, it is used to protect the oxygen OH group or the alcohol group present in the compound. So what happens here? This silicon having this strong affinity for this oxygen, so oxygen will get bind strongly to silica and we are getting the corresponding silyl compound. SN2 type of the reaction occur. This oxygen having the negative charge, it will attack this silicon and this chloride minus ion will get removed and we are getting the corresponding silyl enol ethers. These are called as the silyl enol ether, or the alcoholic group is protected by now silyl function group. So this is trimethyl silyl function, it is attached to the oxygen. It is also can be indicated as, and the another enolate we can write this as, for the E-enolate we can write it as simply OTMS. We can write this trimethyl silyl group as the TMS. So this type of the two enolates are now protected And now we can separate this protected form of the enolate by the column chromatography. So after separating them by column chromatography, we can remove the silyl protection. How it can be removed? Simply it can be removed by reaction with the fluoride minus ions. So this fluoride minus ions having the strong affinity for the silicon, then oxygen, strong bond is formed. So this fluoride minus ion attacks the silicon and this bond undergo cleavage. So we are getting the corresponding Z enolate in pure form. So we are getting the separate Z enolate here, or enol, or it may get protonated. So Z enolate is formed and corresponding trimethyl silyl fluoride compound, it will get removed. So in this way we are getting the corresponding Z enolate separately, and again if we treat the fluoride minus ions with the E enolate, we are getting the E enolate separately. So we are getting these two enolates. Now we can control this diastereoselectivity in the reaction. How? If we treat the carbonyl compound or aldehyde we have taken here, if we have generated enolate from this carbonyl enolizable compound. So if we treat this electrophilic aldehyde with the Z enolate, we are getting the syndiol. And if we treat the E enolate, pure form of the E enolate, only E enolate with the aldehyde, we are getting the antidiol. So we can form one diastereomer selectively. Now let us see why this is happening, why we are getting the syndiol with the Z enolate and antidiol with the E enolate. Let us see this reaction. So some reagents we are going to use that will specifically generate the Z enolates. So one of the reagent or the compound for this, it is the tributyl boron triplet compound or trialkyl boron triplet compound. This type of the compound will they having the good leaving group as the triplet ion. Triplet, it is the good leaving group, and boron we know that the electron deficient molecule. So it will react with the oxygen atom, and this type of the compound in presence of base like diisopropyl ethylamine in presence of diethyl ether at very low temperature minus 78 degrees Celsius. Under these conditions, what we have used? The boron complex or boron compound we have used with the good leaving group. In such a case, we are getting nearly 99% of the Z enolate is formed. So selectivity for the Z enolate is more when we use this type of the boron compound. So we can synthesize Z enolate in the major product or the high yield, more than 99%. Now this is the Z enolate formed in this reaction. So we have taken the example of this 3-pentanone molecule, 3-pentanone. So this 3-pentanone molecule react with the dibutyl boron triplet with the base in the ether at lower temperature. We are getting the major amount of the Z enolate is formed. So this Z enolate react with the, here it react with the corresponding carbonyl compound used. Here is the propanaldehyde molecule. So propanaldehyde molecule is given, how it react. So this enolate having negative charge, this carbon is nucleophilic in nature, and this is your aldehyde group. So what happens? It attacks the carbonyl group and the corresponding aldol is formed. So major quantity we are getting the syn aldol. So higher amount of the syn aldol is formed because this compound, boron compound, generate only the boron compound will give the Z enolate. Now, so selectively we can form the Z enolate and syn aldol compound by using the boron compound. Now let us see why this is happening. So for this we have to consider the R1CHO, this type of reaction. This is the Z enolate generated from the boron compound. This is compound first, and the two types of the transition states are possible for this type of reaction. So when we reacted with the aldehyde group, here the chair-like transition state is formed. How this transition state is formed? Here is the aldehyde group. We can see here. Okay, here is the aldehyde group. This aldehyde, it is slowly going to react at this carbon atom. This is the reactive nucleophilic carbon atom, and this is the next carbon atom. Okay, and this is oxygen and boron. Oxygen and boron. So this molecule, this enolate, will arrange itself in the chair-like conformation. So as these two molecules approaches each other, this stable chair-like conformation is formed. So here boron is slowly going to attach or interact with the carbonyl group of aldehyde, and this carbon is going to react with this carbonyl group so as to form the new bond here. So this chair-like transition state is formed. So in this case we can observe here this first second transition state, and another possible transition state is that in which this enolate, Z enolate having the same orientation, we have to change the orientation of the aldehyde only. Here aldehyde R1 group is above the plane, hydrogen is below. Here hydrogen is above and R1 is below. So in this case what happens? This R3 group which is present at this position, here hydrogen and R3, they are close proximity with each other, and here R1 group of the aldehyde and R3 group from the ketone is closer to one another. So as this R group are bulky, there is clash or the steric hindrance, repulsion occur, interaction repulsion occur. So clash for this R3 and R1 occurs. So therefore this transition state becomes highly unstable, and this transition state always give the anti-product. So anti-product is found to be minor, or it is not formed in this, or it is formed very trace amount, very less amount. So this, as this is the stable transition state, from this the syn product is generated. So that's why we are getting only syn product for this Z enolate only. So Z enolate gives the syn product because it is formed via the stable transition state second. So this is the stable orientation, low energetic orientation for the two molecules, chair-like transition state. Now again same condition can be applied for the E enolate. E enolate will give it will form the again two types of the transition state. Only the difference is that in that case we have to change this orientation. Hydrogen is there and here is the R2 group. So in this case what happens? This second compound, this transition state, and in this transition state what happens? This hydrogen becomes here and this becomes R2. So again this type of the for this type of the transition state, clash is there. So this become unstable, and that will give rise to corresponding syn diol for E enolate, and the stable transition state gives rise to anti-diol for the E enolate. So this is the basic reason which is given from the stable transition state, and thereby we can generate these stable compounds. So this explains the diastereoselectivity of the reaction. So we can direct the reaction by using the generating corresponding either Z enolate, that will give the syn diol, and E enolate will give the anti-diol. So this is the last topic from the asymmetric synthesis. Now we will stop here. Thank you.